Okay, so this project is about testing the primality of a sequence of integers. So as part of a program, we'll be generating a sequence of random integers of a given size, given array size. And for each integer in that array, you're going to find out whether they're prime or not using two design strategies, dynamic programming combined with binary search and brute force design strategy. So for each of you, I have assigned n value, which is called the total prime count, which is nothing but the number of prime integers you are going to find and develop a table based on them. And then the size of the randomly generated integer array, we're going to vary that for different values, 10, 100, 1000, and so on. Okay, so the let me give more details about the two design strategies now. So we have the first one is a dynamic programming combined with binary search approach. So this we are going to do it in three phases. The first phase we are going to construct a table of the first n prime integers. So for example, if I given a value of 10,000 for someone, it means you are going to construct a table that has the first 10,000 prime integers. So the prime integers are like, for example, 2, 3, 5, 7, 11, 13, 17, and so on. So 29 is actually the 10th prime integer in this sequence. So like that, you are going to generate a table that has all the prime integers, and for each of you I have given the number of elements that are going to be part of the table. So you're going to find a table that has 10,000 prime integers, the first 10,000 prime integers, or the first 15,000 prime integers, and so on. So in this small example, I have basically given you, or we have constructed a table of the first 10 prime integers. Okay. So the way we are going to do that is using a dynamic programming approach. We'll see that with more detail as we proceed. Now, once we construct such table of prime integers, we are going to find the maximum value in that table, which will be basically the nth largest prime integer. So we call that as P max. So then in the second phase of this design, what we're going to do is basically generate a sequence of random integers. The number of elements that are part of the sequence is given by this m value. So if I say m is 10, you're going to basically generate a sequence of 10 random integers, and the values of the integers in the sequence is going to be in this range from 2 to p max plus 1. Okay, so p max is based on the previous phase where you found the nth largest prime integer. Alright, and so once we construct such a sequence of random integers, in the third phase what we're going to do is for each integer in that sequence, you're going to find out whether they're prime or not using a binary search approach. Remember, in the first phase, when you construct this table of prime integers, the first 10 prime integers, this is going to be a sorted list, because you're going to find, as I show here, the prime integers in the sequence. So it's going to be a sorted list. So you know, with a sorted list you can do binary search more efficiently. So you're going to search in this sorted sequence whether a given integer is there or not. If it is there in this table of prime integers, then the integer you're searching for is also a prime integer. Otherwise it is not a prime integer. That's the way you're going to go about it. Now, in the second design, what we are going to do is we are going to make use of a property to test for prime integers. That is, if you want to test whether an integer p is prime or not, you may be wondering, a brute force strategy is to check whether there is any integer from 2 to p minus 1. So for example, if I want to check whether this 29 is prime or not, the brute force strategy you might be thinking is I can check if any integer from 2 to 28 divides 29, then that integer is a factor of 29, and then 29 is not a prime integer, right? So that's the way approach you will take. If no integer in the sequence from 2 to 28 can divide 29, then 29 is prime. But there's a theorem that states that you don't need to go all the way to p minus 1 if you want to find whether p is prime or not. All you have to do is go from 2 to square root of p. So for example, if you want to find 29 is prime or not, you have to go only up to 2, 3, 4, 5, because if square root of 29 is no greater than 6, it's only greater than 5. So if you test from 2, 3, 4 up to 5 and none of these integers can divide 29, then we can say 29 is prime. Okay, so that's the property you're going to make use of. So what we're going to do is you're going to find out the p max value based on the phase 1 of design 1, basically depending on how many prime integers you're finding out. The nth largest prime integer, the p max, will be used in this design also. So we have to do at phase 1 of design 1 to do design 2. So here we are going to then generate again a sequence of m random integers from 2 to p max plus 1, and then for every integer in the sequence you're going to use this brute force approach to test whether that integer is prime or not. So in both these cases, what we are going to do is in the first design for the third phase, where we use a binary search approach to find whether every integer in that given or not given the random sequence of integers generating is prime or not. For the whole sequence, you're going to measure the time, how long it takes. Similarly, in the second design, again for the whole sequence of random integers, you're going to find how long it takes for the entire sequence to determine whether for each integer in that sequence whether they're prime or not. Okay, so that's the overview of these two designs. Now let me go more detail into the phase 1 of the first design, where we do this dynamic programming. So the idea is, again, you're given this the number of prime integers you need to find. That's called the total prime count, or n, that's given to you. So if you're given 10,000, you're going to find a format table or construct a table of the first 10,000 prime integers. So we're going to start with number 2. You know, in 2 is a prime integer. So the first element in our prime integer list is going to be 2. And then prime count is initialized to 1. So we're going to increment this prime count until we hit that n value, or the total prime count given to you. So also this number is going to be incremented 2, 3, 4, 5, and so on. So for each value of this number, we are going to test whether it is prime or not. If it is prime, then we are going to add that to this prime numbers list. So let me use this case. So how we are going to so let's say 29 is not there, so the table currently has up to 23. Okay, so these are the table. This is the table of prime integers you have found so far. So then let's say we want to test for 24. Now to test for 24, what I need to do is I need to just divide the 24 by each integer in this list, in this table, starting from the left one, the smallest one, which is 2. If one integer could divide 24, we can say right away that 24 is not prime. So since 2 can divide 24 and the remainder is 0, then we can say that 24 is not prime. Okay. So now how about 25? We are going to divide 25 by 2, the remainder is not 0, and then we are going to divide 25 by 3, again the remainder is not 0. So now we don't need to divide 25 by 4. The approach we are going to take is you're going to divide them only by these integers. The theorem behind this is any integer which is not prime, okay, any composite integer, that's what it is, something which is not prime is a composite integer, could be written as could be written in terms of prime integers. So for example, I could write 25 as 5 times 5. Given now 24, I could write as 2 times 3 times, which is 6, and then probably another 2 times 2, which is 2 times 3. So I can write any non-prime integer as a product of prime integers. Okay, so that's a theorem. Any non-prime integer, which is also called a composite integer, could be written as a product of prime integers. So if I want to test whether a given integer is prime or not, all I need to do is divide that integer by the prime integers that are before that in this table. And if none of them, actually there's another theorem which we're also going to make use of, but basically if you cannot divide an integer by these prime integers, then that integer is prime. Okay, so in this case of 25, you could divide 25 by 5, so you can write away say 25 is not prime. Now same way for 26, 27, 28, right? They're all not prime. So now let's do how to do 29. So 29 I'm going to divide by 2, and I can say the remainder is not 0, so I need to then divide 29 by 3, the remainder is not 0, then 29 by 5, the remainder is not 0. Now do you think we need to again divide 29 by all of these other prime integers that are out there? The answer is no. The reason is, remember, even in the brute force approach, what did I say? If I want to test whether P is prime, right, to test whether P is prime, you need to divide P by integers 2, 3 up to what? Square root of P. Okay, so in this case 5 times 5 is 25, which is less than 29, but the next integer that is out there is 7 times 7 is 49, which is greater than 29. So because to test for prime you need to only divide that candidate P by anything which is from 2, 3 up to square root of P. That itself is sufficient. So you have divided that. You have divided by 5, and you have found that 29 divided by 5 remainder is not 0. Then the next number you need to try is 7, but 7 times 7 is 49 and is greater than 29. So you don't need to try 7 or 11 or anything like above 5. So which means if you have tried 2, 3, 5, and the next integer 7 is square of 7 times 7 is about 29, then you can right away say 29 is prime. So that's what we are doing in this loop here. If prime numbers list a test prime index times the same thing is greater than the number, then we have come to a point where everything before that could not divide that number, so that number is prime. And then we are also checking if that is not the case. So for example, when I'm checking for 2, 3 or 5, the first if statement will not be true, so we'll go to the second if statement and we check whether that number is divisible by this integers in this table of prime numbers. Okay, so if you find something that is divisible, in the case of 26 or 27 and all these things, if you find the number is divisible by the prime integers that are out there in the table, then we can right away say the prime number is not prime and come out of this for loop. Okay, so if either of these two if statements are true, we can come out of this for loop, and then if the number is prime, we are going to add it to the list of prime integers and increment this prime count, and we need to keep doing this until prime count reaches the total prime count. So by that time we would have found the table of that many prime integers, which is the total is total prime count, the number of prime integers we have included in the table. Okay, prime numbers list. So the last integer in the prime numbers list, so if you form a table of 10 prime integers, that's going to be 29 over here. So this is a table of 10 prime integers, so your P max is going to be the last integer in that list, which is in this case 29. So in your project, when you construct a table of 10,000 prime integers, the last prime integer is going to be your P max. So we need to know this P max for each of your n values. Okay, so once we do that, in the second phase we are going to generate an array of m random integers. So for everyone I have given the same set of m values, 10, 100, 1000, 10,000 and so on, and the values of those integers will be in this range from 2 to P max plus 1. Now, once we generate that sequence of random integers, what we are going to do is in this third phase, we are going to test for each integer in that sequence whether they are prime or not using the binary search approach. Because the table that we generate in the first phase is going to be a sorted list of prime integers. So if you do a binary search on it, we can efficiently find out whether any test integer is in that table or not. If it is in the table, it means that integer is a prime integer. If it's not in the table, it means it's not a prime integer. So we are going to measure the runtime only for this phase, the third phase, which is a binary search phase. So before we do anything, we are going to, so all these three phases for design 1 should be part of one single program, but you're going to measure the runtime only for the third phase. Okay, so it is sequential. The first phase where you generate the table of prime integers, then the second phase where you generate the random integers, the array of random integers, and the third phase where you're going to implement binary search. So before the beginning of binary search, you're going to start this timer. So system.nanotime actually returns the number of nanoseconds that has lapsed since January 1st, 1970. So it's going to be of data type long. And then you're going to write a for loop and then pick up every integer in this test integers, which is the array of random integers that is generated in phase 2, and find out whether the test int is in this table prime numbers list, and we're going to do binary search. So I've given you the pseudocode of binary search, so you could implement this as a function and then call this function every time you want to find whether the test int is in this prime numbers list. So you do that for every test int in the test integers, and then when you come out of, after you come out of the for loop, you again find the time, and the difference is going to be the time that elapsed for you to do this binary search process. Okay, and so now design 2 is to use the brute force approach. So for this, you again need that Pmax that you found in design 1. So the first phase of design 1. So you're going to use that Pmax and again generate an array of m random integers in the range 2 to Pmax plus 1. That's quite similar to phase 2 of design 1. Here we're going to generate an array of m random integers. Now phase 2 is what is unique for this design. So we are going to now take every test int in the test integers and do a brute force test of finding if there's any integer from 2 to square root of test int that can divide test int. If there's at least one integer, so again the first integer, one integer is sufficient, right? So when you see 2 can divide test int, just stop the for loop there and say and move on to the next integer in the test integers. Okay, you don't need to divide by every integer in this range. So it starts with 2, 3, 4, 4 and so on, 5, 6, 7 and so on, so until you hit square root of test int. If none of these integers can divide test int, then the test int is prime, otherwise it's not prime. So if even one of them, so the first integer that divides test int, then you can stop the for loop there and move on to the next integer in the test integer sequence. Alright, so we are going to again measure the total time it takes to find out, to decide on the primality of every integer in the test integer randomly generated array. Okay, so we are going to get the time for each of your m values. So you're going to get the time for 10 element array of random integers generated like from 2 to Pmax plus 1, that's the range. And we're going to get the runtime for the binary search approach in design 1 and then the brute force approach in design 2. So repeat that for m value of 100 random integers or 1000 random integers and so on. So you're going to plot an XY graph where the x-axis is your m values, the size of the random integer array, and then the y-axis you're going to have two curves, one representing design 1, that is a binary search approach that searches on this table that you develop using dynamic programming, and the second design is based on the brute force approach. So since the numbers here are 10, 100,000 for the m values and also for the runtime, you will also see large m runtime values. You need to plot in the log 10 scale for both the x-axis and the y-axis. Okay, and then you need to interpret how the curve comes out, and depending on the graph how it comes out, you need to interpret the results. and what you observe for the difference in time for the two designs. Remember that you're plotting on a log 10 scale, so the values may be closer. So once you transform to log 10 scale, you can increase your scale so that even smaller differences can be magnified. Okay, so you should be able to interpret the graph. So I need you to run the algorithm, the implementation for each of the two designs, and show screenshots of getting those time values for different m values. So for each student you have in the particular n value, that is the total prime count. Based on that you will generate the p max. The design one will also generate the table for the dynamic programming and all those things. And design 2 you will basically use the pmax and generate the random element array and all those things, right? So I want you to show the results that you get for the time for both these designs, and then include the graph and everything in the hard copy of the report, as well as interpret the graph in your recorded video, right? So we'll stop here.